How do computers see things in images? While it may seem simple at first, teaching a computer to spot chessboards is a deceptively complex problem. You might be surprised at how deep this rabbit hole goes. But stick with me, because this journey reveals some fascinating AI and computer vision fundamentals. And it's exciting to see where this technology is going. In this video, I'm going to talk about some of the ways I solved this kind of problem in the last decade. Jesus Christ. And also I'll talk about some of the ways I used machine learning to solve this. And yes, I recently did try YOLO too, because gosh darn it, it's so freaking good. My background is in robotics and computer vision, so of course I chose to tackle this problem with handcrafted computer vision algorithms first. Back around 2014, Jesus Christ, I went with the kitchen sink approach of throwing classic techniques like Sobel, edge detection, Hough transforms, and more at this problem. To a computer, an image is pixels in a grid. Width times height gives us the number of pixels. These pixels are often 3 values for red, green, and blue, which we can convert to grayscale. We're trying to find the 4 precise pixel XY coordinates that are the corners of the chessboard. This gives us enough information to have a useful understanding of where the chessboard is in the image, in a 3D position and orientation sense. Looking at the image, the outline of the chessboard forms an edge where the pixel values change quickly, or has a large gradient. Edge outlines seem promising, as the checker pattern of a chessboard shows up strongly with them. Considering finding checkerboards in an image is one of the classic ways to determine the camera intrinsics, that sort of makes sense. We can calculate these gradients by applying a type of matrix convolution called a Sobel operator, which is a small matrix called a kernel, that we essentially matrix multiply to every pixel in the grayscale image, creating a gradient image. With some extra steps called the Canny operator, we can refine these into a new image that only shows edge pixels as binary 1s or 0s. Following these edge pixels, we can find contours quickly. The OpenCV library has fast C++ implementations of all these operators. Then we can look for a large quadrilateral contour to identify the outline of the chessboard as 4 corners. This is extremely fast, but needs very clean images. Anything blocking the chessboard breaks its outline. Unlike that, our problem is quite a bit more difficult. As there are many styles of chessboards out there, there will be pieces on the chessboard blocking the view of the lines, and lots of other things like people's hands, drinks, shadows, and more obstructing the view in images. Because of these things, we get a lot of bad data when looking at the output from these classic techniques. We can reduce this a bit with some clever erodent dilations. For the math inclined, another way to think of this is we're trying to tune out high and low frequency signals, and tune into the frequency of intensity change associated with common-sized checkerboards in images. But this still isn't enough by itself. Instead of looking for the outline of a chessboard, we notice that at least some chessboard tiles are often fully visible. So what if we look for the outline of a tile instead? Once we found a tile, we warp the binary edge image so that the tile is a square on it, and then count the number of edges in this warped image along the expected locations of chessboard lines as a score. The computer doesn't know which contour is a chessboard tile yet, so we have to try different contours, then warp the image to it, then try and further align this warped edge image to the expected edges for a chessboard at all possible 64 tiles on this chessboard that it could be. This quickly becomes a very large amount of possible combinations that we have to search and score. It's quite a robust method that will eventually find a solution, but it can take up to minutes for some images. Regardless, we are finding chessboards in images now, and technically I was done with my original goal. Yay! But obviously we can't stop here, right? Right. There's some potential here, but we need it to be faster, so we need to reduce the search space somehow. Another idea is that chessboards have a lot of lines. No surprise there. Instead of looking for contours, what if we looked for the lines in the image? In computer vision, one of the first techniques people turn to for finding lines is called the Hough transform. The general way it works here is to exhaustively consider all possible lines that could exist in an image and vote on how likely they are to exist. These votes form a 2D Hough space where the image axes define the parameters of the line, often the angle of the line and how offset it is from some point. Each edge pixel casts a vote for every possible line that could pass through it, so a single point in image space becomes a sinusoid in Hough space. By finding the peaks in this Hough space using non-maximum suppression, we can find the most likely lines in the input image. Then we can try different combinations of lines to try and find a set of 7 rows and columns that fit the chessboard, which is a smaller number of combinations than trying to grow out the tiles of our previous approach. As you can imagine, Generating a Hough transform is very computationally expensive. My first full implementation in Python took around 45 seconds for a 640 by 640 pixel image. We can optimize the algorithm to only vote based on gradient angles at every edge pixel, greatly reducing the number of votes. The resulting Hough image is much cleaner and almost 50 times faster at 2 seconds. So I was feeling pretty clever at this point, but it turns out there's a complicated probabilistic approach that's 200 times faster than that even, at around 10 milliseconds. And the OpenCV library has an implementation of it, so let's use that. Future Sam here. I wanted a rematch with OpenCV, so I went back and rewrote my Python implementations of Hough transform and informed Hough transform in C++. The full Hough transform runs in a little under half a second now, and the informed Hough transform runs in about 26 milliseconds, which is almost twice as fast as OpenCV's implementation of the probabilistic Hough transform. Take that, OpenCV. I will admit this isn't a fully fair fight since OpenCV's implementation gives us the lines directly. Anyway, let's continue. Overall, this approach is faster than Contours and pretty robust, but is not as precise due to some trade-offs in resolution versus speed of the Hough transform. It also fails if the chessboard is small in the image, or if there's a noisy background with lots of lines, causing false positives. So we're not done yet. There's some potential here with this idea of looking at the image as a whole instead of just tiles. Thinking back about the previous tile contour and growing approach, we needed to reduce the search space somehow. As a human, I noticed the correct tiles have alternating colored tiles next to them, and each of their corners is the intersection of 4 tiles with alternating colors, forming a sort of X shape. There's a lot of varied and questionable research on this topic, but the general gist of it is that these X corners are special mathematically. If you look at the image intensities and gradients, they form something called a saddle point. Calculating this saddle point is actually pretty fast using matrix operations, so it's some NumPy and OpenCV magic. I was identifying a bunch of points in images that were probably chess X corners, but sometimes they weren't. To find the right set of tiles, there's a technique called ransack, which basically tries random subsets of points and throws out outliers. We can do the same here. First, we start at a random tile and then try to grow it out to adjacent tiles. We keep doing this, starting from unseen tiles until we've seen them all, keeping track of the set of tiles that grows out the most. This is really cool to watch and does work well, so we have improved our previous algorithm by reducing the search space of possible tiles. However, as I was doing this, I had an idea. Instead of growing the tiles, we could try to fit a grid to the X corners directly. This means we're trying to find a set of points to fit the grid to, instead of trying to grow tiles in an image, which is a much smaller search space. Which does work here, and we do get our second algorithm from this. This one takes tens of seconds per image, and testing it on a couple hundred images off the internet, we see that it handles way more of the outliers. We could stop here, but that still isn't fast enough for video. Calculating the X corner saddle points takes only about 10 milliseconds, but the next step is the expensive one, as we have to randomly choose subsets of these points and try to fit a grid to them, then image warp and score these guesses with handcrafted metrics. Every false X corner point exponentially increases the number of possible guesses we have to try. This has brought us down from the minutes of the previous approaches to seconds now, so definitely an improvement, but we're not satisfied yet. Around this time in the last decade, deep neural networks were taking off, and these things called convolutional neural networks were starting to identify cats in images pretty well. Yeah, seriously, this stuff was really new in the 2010s. It's crazy to think about how far machine learning has matured since then. Anyway, I was thinking, identifying good or bad X corners seems like a perfect use case for machine learning, so let's see if we can do that here. I initially put together a deep neural network classifier in TensorFlow, and the documentation was quite lacking back then, by the way, that took tiny image patches from this list of X corners or saddle points, and gave it a binary classification of positive or negative for a chessboard X corner. And yes, this is pretty overkill for what seems like a pretty simple 2-axis gradient problem. But remember, with all the weird lighting and occlusions and stuff, this problem isn't actually that simple, and the research papers back then mostly agreed with that. Since I already had a couple hundred images with chessboards and a computer vision algorithm that could find them, I had a labeled dataset perfect for some supervised training. Each image gives us roughly 7 times 7 or 49 positive labels, and many more negative samples for all the other points found. After a couple hours of training, it actually learns it, and it does it really fast. Putting this together with some C++ to build a mesh from valid points, we have a system that can run in around 1/5 of a second per image. As an aside, I also spent a little time looking into some C++ optimizations using a tool called Halide, which can optimize these kinds of matrix convolution operations really well, bringing down the saddle point detection processing time to 1/3 of the original, from 15 milliseconds to 4 milliseconds. This was pretty neat. Next, instead of just a classical deep neural network, I wanted to see if convolutional neural network layers made sense here, since we're working with images after all. After trying out a few different CNN architectures, I eventually found one that worked really well, with 96% accuracy. And wouldn't you know it, it's the classic CNN plus max pool pyramid of most classification models you see everywhere today. It's really fun seeing how things that were so new back then are becoming the backbone of machine learning models of today, like UNets, deep segmentation, stable diffusion, and so on. This kind of stuff is so cool. This model runs in around 30 milliseconds per image, sometimes with bad luck up to 200 milliseconds. So while this is doable, it's not ideal for video. One optimization we can do is realize that in a video, the image frames next to each other generally don't change very much. So we could apply a classic key point tracking algorithm, like the Lucas-Canade algorithm, to track the chessboard points once we find it, and that is super fast, on the order of milliseconds. Altogether, the system works in 2 stages. First, it tries to find a chessboard in an image, and once it does, in the second stage, it keeps track of it with the LK algorithm. If it loses track of the chessboard, it goes back to the first stage. And once we put it all together, we get this real-time chessboard detector. How cool is that? I was pretty happy with this back then, and I considered the problem reasonably solved for the time being. We could finally rest. So you're probably noticing that the video is almost over. I'm so sorry. I do have a YOLO chessboard detection algorithm in the works, but it'll take me a bit of time to turn it into a video. But I can't wait to get it uploaded. I had a blast making this video. If you enjoyed this and you'd like to see more like it, please subscribe and let me know in the comments what you think of the algorithm. Thanks for watching, and I'll see you all next time. Cheers!